As you may have heard, the subject of analyzing systemic risks has become a really hot one in the aftermath of the crisis of 2008, 2010. And strangely enough, the scientific impulse came from a financial institution, from the Bank of England. The risk division of this bank was looking at systemic risks, and suddenly on the way they discovered that if banks are interrelated and form a network, the risks related to the fact that they are interrelated can be substantial. And therefore, just to put what we have done in perspective, I will start with the Bank of England view of on the interbank network. Probably that was the only picture they were allowed to show. So anyway, this is an oriented graph. To be more precise, it's an oriented weighted graph where you have transactions on the links, and so you have a borrower and lender, and they are different. Therefore, the graph is oriented, and also you potentially have something related to the nodes themselves, and this is the balance sheet that characterizes the state of the bank, and in the financial parlance you have assets and liabilities, and the requirement is that assets exceed liabilities, otherwise the node is declared bankrupt. And there is of course a condition that you can write with respect to solvency of a given node. And the only important thing here is I mean, everything is obvious in the sense that you have liquid assets, so it's not really relevant. It's something that is related to exact definitions of what comes into liabilities or assets. What is interesting here is this phi, which tells you in the language of Guy and Kapadia, who wrote the very influential paper on the subject. Phi is the fraction of contracts going bankrupt. So you have links to the node, and what you somehow assume, the process that you study, is that one or more than one node goes out because of bankruptcy. And then it deforms the balance sheet of the neighbor. And if the balance sheet is critically deformed, the next node also goes out. And this may potentially lead to cascading failure in the network. And this is one simple, this is not the only one, but one of the important systemic risks that are analyzed in this. Q is if you have, for example, a building and you want to sell it immediately, then you lose some money. So Q less than 1 is the measure of how much do you lose on the fire sale. Yeah. Well, in that sense, fire sale always brings some illiquidity into the process. Now this is only for beauty, because of course they put Q to 1 in any real calculation that they're doing. Okay, and so then they make a very simple assumption that the risks are uniformly distributed over the incoming links. And so this is a very important simplification, as you will see later. And then the capital buffer is random because you have some stuff like stocks, for example, something that fluctuates on the daily basis. So this brings probabilistic element into the game. And then you have a probability of the default. And this probability, so this is a probabilistic process that propagates on this oriented network. And then they look into one of the wonderful papers on the subject. I think they looked into Newman's, judging by the picture. And then you can write it. And then if you assume that the process is tree-like, then you can. It's very convenient to use a language of generating functions because it's immediate. It's easy to learn. Now. And then, of course, you have. I won't go through this stuff. This is pretty standard, and I think it appeared already in the first paper of Newman and co-authors on graphs with arbitrary degree distributions. So then you can calculate the point at which the percolating cluster appears. And an interesting thing in this particular case is that you have a whole window of parameters in which you can get this effect, and then you assume something, for example, 5% of the, for example, that some banks go out, and then you look at the resulting clusters, and you are interested, and you define contagion as the case when more than 5% of banks die out. And what struck these people was that although that there are events with probability looking small, but the event is drastic. And when with small probabilities, say 50% of your banking system goes out, then this is a risk you have to think about. And this is something new for these people because they are so used. First, they're used to representative agents, not seeing each other and saying only Russian auctioneer, and second, they hardly know any distribution but Gaussian, because they are trained so. And so when you make this small step outside of the business school manual, then when you see such an effect, then of course you have to worry about. This was a kind of a bombshell at that time, the appearance of that paper, and people started thinking very seriously, and all of a sudden, that was 1910. Pardon, 2010, of course. Yeah, 1910 is too early. 2010. That was a direct consequence of the discussion after the crisis, because one of the things that was really apparent after the crisis is that the contagion propagation. If we don't discuss instruments, because in that case these were more derivatives than anything else. But if we just look at the skeleton of what's happening, then the first thing to do is something like this. And so this was analyzed, and this paper caused a flurry of other papers looking at various effects, like overlapping portfolios and others. And also they did some analytical calculation with what they did was the simplest Erdős-Renyi case. And then for small average degrees, everything worked perfectly, and at large degrees, of course, it did not, because the Poissonian distribution is not too good for studying hubs. Anyway, this was the paper that pushed it, and then if you start thinking about it, and if you're a theoretician like myself, you say this is all nonsense because it cannot be tree-like, and you have so many effects in the game. And for example, you can have different motifs in the graph, and each motif can play an important role, and you don't know which role which motif can potentially play, and so on. So we started So we started with my PhD student who works at the Bank of Russia. That's why we have real data. I mean, the paper of these guys was simulation. And now what we did, we wanted to look at real data, which I will describe to you, that we have from the Russian interbank market to understand what is important and what is not important for mathematical modeling of what's going on there. And we started with, you saw the picture of the English, the Bank of England view. So this is the CBRF view, which is much more colorful. This is the Russian interbank network. And the size of the blobs tells you how intensive is the process of borrowing or lending. And so to describe you the data, these are uncollateralized interbank ruble deposits, like of all maturities. We use the data from a period of about a year. And this is, as I told you, an oriented weighted graph with weights of liabilities, and you fix the sign in some way that is appealing to you. Now, for us, positive sign was when the bank I had liabilities with respect to the bank J. So outgoing correspond to liabilities and incoming to claims, and this will be illustrated. Now, the first thing that you look at is what is the degree distribution, the in and out degree distribution, and this is scale free. I will show you the plot later. Now, the definition of vulnerability is no. Yeah.
I have a question about this. This is a weighted graph, right?
Yes.
It's weighted by the liabilities,
Yes.
or the.
Yeah, the
now you
magnitude.
say that it's scale free. Do you have? Because I could have really, really small liabilities, so that it's
No.
effectively
Scale free in the degree.
in the degree. I see. Okay. Okay, because
Yeah.
I could say something is not connected if the
Yeah.
weight is
It's-
below a certain
no,
amount.
it's only no, it's not weighted topology. It's the topology. So it's just the in and out degrees.
And so you're not counting the weights at all.
We
when you
are
talk.
counting the weights because we want to see who goes bankrupt. And so let me
Okay,
go
yeah.
through the procedure, because this, I mean, building this model was the actual game. Maths that came out of it is rather simple, as it turned out. Now, we don't have an abstract criteria. We have a criteria from the Bank of Russia that tells you when the bank goes bankrupt, and we know all liabilities and everything on this graph. So at any given moment, if we freeze one node, then we really know what happens to the neighbors, because we have all the data. We have balance sheets, relevant balance sheets. We have assets, everything. So we can really see how this process appears. Now, why it is interesting? Usually, you would think, mathematically, so to say, that only weights are important. This tells you that there is something more general about these financial graphs, namely the nodes can have important characteristics, and so you have to compare something that you put on the link to something that you have on the node itself. It's like in the epidemic process, you start to take into account how healthy hereditary, say, is this node. So there is something, I don't know a name for it, but this is something more general than a weighted graph, and this is important. So this answers your question. So both balance sheets in the nodes and this liabilities or whatever, take any sign, everything is important. So the computation is in this sense real, and so we just compute this coefficient, which is not h1 but n1, strangely, and So for Russian audience, all the letters here are Russian, actually. This is how the central bank defines this thing. Here, and so just don't well, you don't have to look at it. It's just we use we really use the procedure that the bank has formulated for these cases, and there is a standard condition for insolvency, which is 10%, set to 10 or 12%, depending on whether it's a bank or not. And this is what we really check by putting some. Well, actually, we have put all the nodes and then collected the statistics. So you assume that in your simulation you assume that the nodes go bankrupt, and now the first thing that you do is, if you compare to that simplistic thing, the generating function that these guys wrote didn't know about the bow-tie structure of the graph. Now this can be unimportant or important, but you cannot neglect it. And the first thing we saw is that this is the number one feature of this financial graph, because you see that the distribution is very uneven. So this component is relatively small. In component is relatively big. In out, so that the component that joins the two, in the middle you have both types of links. And here are standard deviations. You see that this is quite a stable feature. So you compute this day after day after day. You know the number. You know these numbers, and so you see that this graph is really uneven in that respect. So if you want to study your cascading can start here or here, and this can be important. In fact, this will be very important. You will see. So already at this point, it was clear that the language we should use should explicitly take into account, even if it's a tree, which will be the case. You have to explicitly build the techniques that has everything in.
You said there was a significant amount of clustering, and yet you
Yes. No, the tree. I will be very explicit about it. The original graph is not tree at all. It has significant clustering. It has motifs, not only triangles, but also 4-point rings and all that, and which is easily detected by spectral or any other method. Let me come to this. Just the first thing is that one has to be very explicit about the origin of the cascade. And naively, of course you will say that this is the most important component, and this will indeed turn out true. Now to the degrees are funny. You see, they are very, very different. And this is somehow a feature that always comes up. We looked at our previous analysis referring to the period before, studied here, also gave approximately at least power-like tails. Now, there's always a question of what you do here, right? How do you put this line? Do you put it like this? Or do you put it like this? Here it's more or less clean. I mean, there is nobody, I don't think anybody knows what to do with this. First, because of the cutoff that is always present, which Sergei discussed in the first lecture. And second, I mean, if you don't know which process generates the data, you don't actually know how to put the line. Right? So all our knowledge comes from Gaussian experience, where we know a lot. But this is useful, and this is useful, and it tells you that these distributions are very different, and they are, well, I would say, kind of power-like. Now, it's disassociative in a very strong way. So your language should take into account the fact, the bow-tie structure explicitly, and second, it should keep correlations, at least the correlation of the closest neighbors. This, fortunately, this is easy, as you know, and the generating function language is very easily adapted here, and this was done a long ago. I know the paper of Newman who did it, but there should be others as well. Now, to your question, what is important to us? When we look at the, remember in the English paper, there was only one source of contagion, which was uniformly distributed over the incoming links. And now we're in a position to measure the probability of having at least one incoming link that is contagious for all the situations that are there. And here there are examples of these probability distributions for out starting, so this default comes from out component and goes to in-out, from in-out to in-out, so stays inside the nucleus, or from out to in directly, or from in-out to in. So we have all the cases, and why it is useful. Because when you have the formalism, then you can plug these functions in and check that you get the right numbers for say, the average size of clusters, which we did. But this is, you see how diverse this picture is in reality with respect to this initial simple picture advocated by Gay and Kapadia. Now, I think a very important feature of this is the presence of strongly connected component, and you see that this component is serious. I mean, it's from, on average, 111 nodes in the in-out component, 100 belongs to this SCC. So this is a sizable, compact structure that sits in the middle of the bow tie, and of course determines many of these properties. What's interesting that you see that it grew in size, and we don't quite know how to interpret it, but this is a fact. Now, what you do with this, you just take a pen and honestly write the matrix, so to say, structure for the generating function that has all components in. Just you have several functions that describe you the contagion. For example, here starting in out and going to in directly, and then you from within this node from which to which you arrive. You go from out to in, arrive at a certain node, and now this node can have additional links coming from both out and out, and so you just have to write it down. And we wrote it down for all these cases, which is, I mean, it's clear how to do it. It's just a little laborious when you start doing it, and then you get accustomed. And okay, and so we did all this, and then so we wrote all these generating functions, and this formalism explicitly takes into account, as I told you, it does explicitly take into account the correlations of the nearest neighbors, and then the average size of default clusters is given by the familiar derivative at point 1, and of course we have analytical expressions for this. Now this has several components. When you differentiate it, you have several contributions, and some of them are actually consistency equations, so you have to solve them. As usual with correlations, this procedure generates you equations that you have to solve, not just pure derivatives, but these are lengthy, and so I decided not to show you these things. And now we're coming to the results. First, the result really does really strongly depend on the out degree of the initial node. This is the fact number one. You see, this dependence is, and you see, what you also see here is that something that is coming from in-out cluster is superior always. So in terms of the contagion process, yeah, actually I forgot to mention it at the right place. When you look at the structures that you generate by contagion process, they are always tree-like. So you see, so there is how to say this default graph, so to say, which is something that you derive from the original one. So there is some kind of transformation that transforms the original graph into something that is important to the process of default propagation. Now, this is always tree-like, with extremely rare exceptions. This is an experimental fact. Now, out of all graphs that we had, 1 or 2 contained loops. And everything else was tree-like and very modest in size. Maximal size was 3 steps. There was never anything more than this. So in reality, all the possible complications, and in the particular case of the Russian interbank market, now coming back to a question, it's very difficult to say about something about, say, German or US market. You have to use the data, because this may look different.
I have a question. So there is this paper by people in New York, Duncan Watson, some people who looked at contagion processes in general, and they found that most things, I mean, we think of a viral spread as something which starts with a node, then it goes to 5, and it grows sort of at some rate, so from maybe a constant multiplier of 1.3. And they found that that is actually not the case. If you look on typical viral processes you see on sort of social networks, or many they studied actually, they all seem to have what you described. They're sort of either sort of die very fast, or they sort of within 2 or 3 things they have reached everything they could reach.
Yeah, it's very.
It seems similar here.
I don't know. I would take the reference, because thank you for this for this comment. It may be a generic feature. It's you see, of course.
That was an experimental result also.
Yeah. You see, what I personally wanted most is to understand why it is so. What in this viral propagation selects tree structures? There should be some underlying principle. I mean, that such things never happen occasionally. Now, unfortunately, there is absolutely no picture, neither game theoretic nor anything else, explaining you what the hell these guys are doing. I mean, why they are lending money, except for the fact that all of them want to be rich. But you don't go very far with this scientifically. So if it is the case for other social networks where we can build, where we can have more understanding of what's going on to the nodes. For example, if we would have some game theoretic understanding of the local game, this would be sufficient. If you play with your neighbors and make some decisions, and if it helps you to say that no, say the rings are out. So there should be game theoretic things like Jackson-Walensky that quote unquote that's help you to select topologies. But that's a very interesting question, and unfortunately I don't know what to say here except for the observation, but I will gladly take the reference. Yeah, thank you very much. And so you see, this is a very dramatic difference, as you see. The size, here we have a distribution of the sizes of these clusters. I mean, overall the effect is not dramatic, as you see, but what is dramatic is the difference between the clusters generated from the kernel, from the nucleus, and from the left side of the bow tie. So it's clear the number one effect that you see immediately. And so if you want to be quantitative, well, I think two things are vital. First is the bow tie, and second is the dissociativity. And here are my conclusions, our conclusions with Zhenya Rumentsov. So the bow ties is essential. Now the original topology is complicated, but the default clusters turn out to be tree-like for some magic reason, and this allows to generalize known techniques and write everything down, lengthy but simple. I actually hoped for more here, but well. And also what's important, that at least this type of contagion is relatively harmless. So this particular effect is small. So what looked theoretically like a big menace turned out to be a balloon. Well, at least in this case. And as far as I can understand, this is close to the conclusions that other people arrived at, although this analysis is rare in the sense that the data is very detailed. And this is quite unusual. I'm aware only of one analysis of comparable accuracy. This is the analysis of Brazilian market done in Columbia University by Ramakont and his student. Thank you very much.
So we have time for a few questions.
Okay, I just have some very naive question.
Wait.
Okay, I think
He's loud enough.
a naive question. So you have some model of contagion based on these formulas. Is this do you have some data, kind of experimental evidence, if it's possible or whatever, that shows that this type of contagion is really a realistic mechanism, is really the danger for actual? Because, you know, there are some things which are not included in this dependency. For example, I don't know, imagine that our de facto government will issue some law, and this can, because of something, triggered by some event.
The central bank is not there, as you might have seen.
Yeah, so...
Is not.
So how realistic,
Well,
is it your opinion?
you can't...
What is the relation between theoretical analysis and practical?
I mean, this was a very, very practical analysis. You just take the banking network as it is. You analyze certain types of loans, and you ask whether the bankruptcy of any given node can lead to something, and this is the question you ask, and then you get the data. So you get the distributions. These are not from the formalism. The formalism gives the same, because it's accurate enough. But this is experimental.
No, this is just experimental about some sizes. But there is a...
What do you mean?
There is an effect of contagion, which is not
There are other types of contagion.
So my question is, are there any data which show that support the idea that this is something worth analyzing? This is a realistic scenario, and most important thing.
No, I think this was. I don't think this is an important source of contagion, and our analysis have shown it.
Oh, so now after you have done this, you can forget about this type thing and start another.
Just could you please read it here? You're welcome. The initial condition is you assume that one bank defaults.
Yes, but which one?
Oh, this is you take, yeah, no, it's, well, it's not random in the sense that we make bankrupt all of them were made bankrupt artificially, and then the most important thing is you have to decide what happens, well, and then you see what happens to the neighbor, right? And then you get an average picture. And these are the average pictures of all days, all possible bankruptcies.
Yes, so that you average over all possible initial.
Yes, yes, yeah, and
So that, but
yeah, yes.
there is, you know, this famous bootstrap calculation problem.
Yeah.
Where you, in principle, you make something similar, but you start with a finite fraction, randomly chosen.
Yeah, you see, it's in the case of banks, it's highly unrealistic. I mean, it's very difficult to imagine a situation in which 5 banks go bankrupt, for example.
But if you consider simply a finite size.
Academically, I mean, you see, what I was really interested at was what is the relevant mathematical model for the concrete episode, and I think that the most important message was that topology doesn't matter. Only.
Yes, but the process is the same as in the bootstrap.
That's right. Yeah, that's yeah. By default, yes, that's right. But I mean, this is the. I would say that this is the only natural way this could have been done.
One more quick question.
Okay, I have a question on the length of the cycles in your original graph. The reason I'm asking is that I'm wondering which one is sort of cause and effect. If you say that all cascades are essentially lengths depth 3 at most.
Yeah, and they're trees.
So if they're depth 3, if there would not be trees, you would need very short loops. So maybe your graph has loops, but not that short ones, or not that many short ones.
It does. I mean.
So is that a possible explanation, or does that not work?
Yes, you could explain it in that way, but somehow at this point we lost interest. We have the spectral analysis, and we don't even want to include it into the paper, because well, on the surface, yes, but because we don't have a good understanding of the sense of all this. Mechanically, for describing the contagion process, this is sufficient, and you see it. And so something mathematically more involved should be reserved for other problems. I would say that I would really expect that in problems like opinion formation, with several states, with a game theoretic formulation, one would really worry about loops of various sizes, and this will be extremely important. Type of pots type, the effect of loops of various size, and there are many fine effects related to loops, but this is, for me, this is not a place to think about it. That's why. Although we have the statistics, because of course we did the spectral analysis.
Okay, let's thank
Sorry,
Andrei
yeah.
for a very nice talk.
Thank you.